So now let us come to see a practical design of antenna, which actually Professor Girish Kumar and his student, they have done this design. So what they have done is they have designed a horn antenna, and they have fed it appropriately. Now when you look at this design horn antenna design, what is important is that we have to excite the dominant mode, which is TE10 mode. Now you know in the waveguide, if you have to excite the TE10 mode, then the waveguide is to be fed along its center line of the width. So consider the width, find the center point, then draw a line along the z-axis in the center point. On that line, you have to feed the waveguide to excite TE10 mode. The reason is along this line or around this line, most of the power in the dominant mode is concentrated around this line, around this center line, crossing the center of the width of the antenna. So around that, maximum power is concentrated, or most of the power is concentrated. So if you give the feed there, so most power will come to that point. So from that point it will be distributed. If you feed at any other point, so the most power will be at the other point, which will degenerate or dissipate. So it will not come, most power will not come to the center point. So at the center line, along the center line, power will be minimum. So that is not desirable. So how we do this, usually we put it at the center. So that is what is done here. We can see there is a coaxial cable at the bottom. You can see there is a coaxial cable or a coaxial feed which is connected to the antenna. Look at the antenna. The front face that you are seeing is open, which is the aperture of the antenna. The back face is actually closed, the waveguide portion. The back side of the waveguide is closed by the metallic, which means we have an electrical wall there, or which is a short circuit. Okay. So on the back we have a short circuit, on the front we have an open aperture, and on the waveguide at the center line of the width of the waveguide we have put a coaxial probe. Let us take a side view of this antenna. If you look at the side view of this antenna, on the back we have the short circuit. The height is B because we are exciting it in the TE10 mode. So since you are exciting in the TE10 mode, the probe will be on the width of the antenna. So the portion, the width of the antenna, that will through that the probe will be fed to the antenna. So not through the height of the antenna. So B is there through which the probe is not coming. Probe is going through the A part. So it is at the center of the antenna. This is a cross section through the center of the horn antenna. So now if you look at this antenna, we have this picture shows the face center, the neck to mouth length, or the length of the antenna, and from the face center to the edge. Everything is shown here, as well as the aperture. So these are RE, rho 1 and rho E. What are these things? These are shown here. Then let us and small l is the length of the coaxial probe. Now let me discuss about the coaxial probe. It is like a coaxial line. Coaxial probe is a coaxial line, but the probe is feeding the antenna. So what happens is a coaxial line comes up to certain length. Then after that, the center conductor protrudes beyond the coaxial line. So if you look at the coaxial probe here, we have a coaxial line which is the larger cylinder. Then from the top of the cylinder, there is a protrusion or an extension of the center line of the coaxial probe. So there is an outer conductor, there is an inner conductor. Between the outer conductor and inner conductor, there is dielectric. The inner conductor protrudes outside the coaxial probe. Now this protrusion portion is actually feeding the antenna, the horn antenna. Now on this protrusion portion, if you look at this, first let us look at the outer side. The outer side or the outer conductor is connected to the antenna metal, which is the outer side of the antenna. So to the metallic part of the antenna, the outer connector is connected, and the inner conductor protrudes inside the antenna, which is free space or dielectric inside the antenna by a distance L. We will see how much L is to be there, what should be there L, but it comes by a distance L into the antenna. So the outer conductor is grounded. It is like connected to a ground because it is outside is the metallic part, so it is connected to a metallic part. So metal part acts as a ground. So outer connector is connected to the ground. Inner conductor is carrying the signal into the antenna. This can be more clear that inner conductor is not connected to any wall. If I take a top view, so let us take a top view. From the top view, you can see the inner conductor protrudes at the center. So look at A. A is the aperture. So A by 2, if I draw a line which is rho by rho 2, so along that line, if I draw a line, extend that towards the antenna, on that line will be the center conductor. So on the dot within the circle is the portion from the central conductor. So that gives you the top view. Now that portion is at a distance of DSC. DSC stands for the short circuit. So edge is short circuit, back edge is short circuited because we have a conducting wall. So it is at a distance D from the short circuited wall. So it is called DSC. WLG is the length of the waveguide. WGL. WG is for the waveguide. L is the length of the waveguide. So that is what it is. Now, if we have a short circuit at the end, then from this short circuit, there will be reflection. Because of the reflection, once you start exciting means that is the input point. So from that point, it will go in all directions. The radiation will go in all direction, or the electric field will go in all direction. From this short circuit, it will be reflected back and come to that point. So that will be loaded. The feed will be loaded. To avoid the loading of the feed, what we do, or what is done by many people, when you design the feed, what you will do is put it at a distance. DSC should be approximately lambda G by 4. So if it is lambda G by 4, you know, a short circuit transmission line section of lambda G by 4 has an input impedance which is equal to 0. So is converted to an open circuit. So if it is lambda G by 4, if it DSC is approximately about lambda G by 4, then at the probe point, it will show an open circuit. Since there is an open circuit, there is no loading. Open circuit does not load anything, so there will be no loading. So DSC should be approximately lambda G by 4. So when you design, this is one point that you should remember. Then what is the protrusion of the central conductor into the antenna? Now if you look at that protrusion, a protrusion portion is actually like a monopole. So if it is like a monopole, the length of the monopole should be such that the monopole is radiating at the frequency in which you want to excite the antenna. And why it is a monopole? What is the advantage of using monopole? Monopoles are usually broadband antennas, and the horn antenna is also a broadband antenna. Therefore, that is an advantage. And length of the monopole is usually like a dipole. Length is half wavelength. Monopole will be lambda G by 4. So it will be should be approximately equal to lambda G by 4. Now let us look at the design parameters. The design parameters are shown here. Capital A is the aperture width, aperture height, waveguide width, waveguide height, then waveguide length, horn length, RE or RH, then probe length L, which is monopole, that you can see probe length L is equal to 75, which is less than the aperture height. So it can easily be accommodated within the waveguide, since it is less than the waveguide height, which is 120. So it can easily be accommodated within the waveguide. So L is calculated as lambda G by 4, slightly less than lambda G by 4. Then R is the probe radius, DSC is the distance from the shot. Now how these are calculated? First, the center frequency is taken. Center frequency means first you find out in which range the antenna is operating. Then from that range, find out the center frequency. In the center frequency, we calculate these values. These values are calculated for second frequency. Now let us consider what are the effects of these parameters. Effect of the probe length or L. You can see as we change the probe length, increase the probe length. Since we increase the probe length, and then our probe length is in terms of lambda, and lambda is inversely proportional to F. Therefore, if you keep on increasing lambda, then F will decrease. So you can see that as we increase the probe length from 70 to 80, it is decreasing gradually. The frequency is decreasing. At 70, it is at 900 megahertz, and at 80, it is around 780 or 770, somewhere there. So it gradually decreases. So this is the effect of probe length. So depending on our desired frequency, we should fix the probe length. This is one point. The second point is probe diameter. As I have discussed the half wavelength antenna, there also I said that diameter has an effect on the total input impedance. So diameter has an effect also on the frequency. Because of the fringing field, it will have an effect on the frequency. It has a loading effect. Fringing fields have a loading effect. Because fringing fields have a loading effect, and there will be loading, so there will be a change in frequency. You can see as you keep on increasing the diameter, slight decrease in the frequency, operating frequency occurs. So there is no point in increasing this diameter beyond certain value. So we should have the diameter, do a parametric study, consider a diameter which gives you the best matching. So here it is 3.5, that is the best matching, so we consider that diameter. The next is the location of the feed from the shutting point, shutting post or shutting point, or the end of the waveguide, location of the feed. Now as we discussed, the feed is to be located approximately lambda G by 4 distance, so that there will be less loading. So if that distance changes, for example, it is more than that, the distance is more than that, it becomes uncapacitive. So 75, it becomes capacitive. 60, it becomes inductive. As you know, a shorted line is inductive for if certain line is less than lambda g by 4. It is inductive, so you can see 60 millimeter in the Smith chart. You can see it is in the upper part. A major portion is in the upper part. So that shows that it is inductive. 75 millimeter, a major portion is, most of the portion is in the lower part of the Smith chart, which is, it is capacitive. 67.5 millimeter, it is almost along the center, which is almost regional. So resistive, mostly resistive. So that is the point, that is the feed location which is required by us. Okay. Then come to the horn length. If you keep on increasing the horn length, you can see the efficiency keeps on increasing, but after certain point, the blue or encirclement, you can see there it almost becomes constant. So once you reach that point, there is no point in increasing the horn length, so that only you will consume space without any advantage on efficiency. So you can always increase the horn length up to this point where it becomes start getting constant. So around 200 to 250 millimeter horn length is sufficient for a frequency of 1000 megahertz, 800 to 1000 megahertz. So 800 megahertz to 1 gigahertz or 0.8 gigahertz to 1 gigahertz. For that, 200 to 250 millimeter is sufficient. Then we will come to the next part on the aperture area. So if you fix, once you fix the horn length, then keep on changing the aperture area. If you keep on changing the aperture area, the directivity, you can see that directivity changes. So as you keep on changing, increasing the aperture area, directivity increases, but after some time, after certain frequency, about 1.1 gigahertz around there, it again drops down, the directivity drops down. Why this occurs? This occurs because of the phase error. Phase error parts of the phase error becomes significant, so directivity will start dropping down. So aperture area should be such that this dropping down should not occur. So aperture area in terms of this wavelength should be such that this is the directivity should not drop down. So you do a simulation first, and there you do this. Look at this. So with this, we'll come to the end of our discussion for today. The rest part is on the design of microstrip antenna. We will discuss that maybe in the evening, if it is possible in the evening, if you are free. Otherwise, sometime else, once we get some about half an hour, 15 minutes to half an hour discussion on microstrip antenna, practical aspects of microstrip antenna design, that we will discuss later. So with this, we will come to the end. So we discussed